Welcome to Wireless Future. I'm Eric Larsson and I'm here as always with my colleague Emil Björnsson. Hello Emil, how are you today?
I'm great. It's good to be back with another episode.
It is indeed, and this is, according to my records, episode number 17. That's amazing.
Yeah. It's a great first season that we are getting. I don't think we were predicting to really continue like this when you are almost...
Well, it's always hard to predict the future.
Yeah.
So the topic of today's discussion is going to be on energy efficiency in communications. And as a piece of background here, Emil, you have co-authored a white paper issued by the IEEE Future Networks looking at 5G and beyond. And the title of the white paper, I think, was just energy efficiency.
Yeah, it's some kind of roadmap towards the future that IEEE Future Networks are producing with respect to different topic areas. And our topic was energy efficiency.
Right. So what does energy efficiency really mean in the context of communication systems?
I guess in general, energy efficiency is like you're going to carry out a particular task and how much energy is consumed in order to do that. And that was then measuring how efficient it is if you're comparing different types of solutions. And when it comes to our mobile networks, they are consuming, say, 1 to 2% of the total energy in the world. And then it might only contribute to, say, 1% or a little bit less than that to the carbon emissions. But in general, I would say energy efficiency is important because it causes environmental issues in terms of carbon equivalent emissions, and also it has the cost dimension to it. And since the traffic is increasing with like 45-50% per year, it sort of becomes a concern over time.
Right, so no doubt energy efficiency is important, and I guess there are two aspects here, right? One is the concern over growing, say, electrical power consumption worldwide in data centers and mobile networks and all sorts of IT infrastructure. And the other is also, I would think, energy efficiency of mobile devices that have to run on batteries. Where you're really constrained by the weight of the device and the lifetime of the battery.
Definitely.
So how can we make networks more energy efficient? What are the technical approaches here?
Yeah, I think one can approach this at a few different levels. So one level is when we are planning the infrastructure. How do we deploy our base station? What kind of characteristics do they have? And also when it comes to the user devices, what kind of user device should we have? Then once we have decided on that, we could then go down and think about the active mode when we are actually communicating with the devices, and the standby or inactive mode when they are only waiting to decide on if there is some traffic or not. So one can sort of approach all of these different levels and think about what are the bottlenecks. What is it that consumes a lot of energy, and what can we do about it? Could we turn something off? Can we consolidate different pieces of hardware? Maybe we don't need all of them. If we can gather all the computation at one place, then it might be more efficient, and then eventually also adapt our algorithms in the software in order to make things more efficient.
But I mean, is the network really inactive ever? I'm thinking of even with today's applications, right? Folks using their cell phones all the time, and even when not using them, they are downloading all sorts of updates and other data. So to what extent are the networks really inactive such that components can be turned off, you think?
So there are actually large possibilities for that, and I think one starting point is to think about that we are building the mobile network for two purposes. One is to provide coverage everywhere, and the other is to provide capacity so we can deliver a lot of data at the places where people are requesting that. But in particular at the countryside, depending on the country, you have of course different densities of population. But in Sweden we have a lot of base stations in the countryside that are there so that if someone happens to be there and wants to download something, you could do it. But most of the time there is very little usage there. Then in the populated areas, you are densifying to keep track of the data traffic and to be able to deliver it. But then we have some concept called the peak hour or the busy hour, which is typically that the traffic is 5 to 10 times larger at particular hours of the day compared to, say, the nighttime. And this could be different to different parts of the city depending on if it's a residential area or a place with offices, for example. And then even if you zoom in at the particular millisecond, the burstiness of traffic that comes from the internet, the IP, TCP/IP protocols are creating burstiness. So even if you average over time, see that there is a lot of data there, at every millisecond it might go up and down.
That's an interesting point. I mean, but isn't that really an artifact of the TCP/IP protocol? I mean, granted, it's a very useful protocol for lots of different services, but there might also be services that are more naturally circuit switched, and in which case you would, with a different protocol, not necessarily see this, shifts or in traffic intensity or peaks in intensity. So how about future traffic types that we envision? I mean, beyond 5G, right? With massive machine type communication, what that really hits on for real, and augmented virtual reality perhaps, and well-connected cars. And, we spoke, I think, in a previous episode about how wireless communications infrastructure could be used to support machine learning applications, and one of the conclusions there was that the nature of the traffic might be entirely different as compared to what we are seeing in the networks today. So what do you think of future traffic types? Will we still have see this phenomenon that the infrastructure is idle much of the time so that it can be components can be turned off?
I do think that the new type of traffic, as you were pointing to, that could be more deterministic in that you're on purpose to make things more efficient. You decide on in advance at this particular millisecond you should be transmitting or so that we could schedule things more effectively. Then at the same time, the bulk of the traffic in today's network is video traffic coming over the internet, and it's not so easy to change the TCP/IP protocol. And there's also a lot of delays created over the internet because things are floating between different servers, so we won't change all of that. So I think a lot of the problems will remain.
Absolutely. There's a lot of legacy here that imposes constraints on what can be easily done, right, on the, say, wireless access layer. In any case, now, if we accept this fact that traffic intensity varies heavily over time, how do we best exploit these variations?
Yeah, I think the good thing is that there is a statistical modeling possibility, because even if there is randomness due to things happening on the internet and due to user behaviors, there is also a predictability in terms of it. So we can predict that at certain hours of the day there will be more traffic, and in other hours it won't. And this can be utilized to adapt how we are running the network. So one of the basic things is to consider sleep modes of different types. So if we are not expecting the device to be active for a particular amount of time, which could be only a few milliseconds, then you can turn off pieces of hardware that is just going idle and save energy from doing that. The cost for it is really that you're creating longer delays when you are trying to contact the device, or if someone wants to contact you, they can only do it at particular predefined intervals. So there is always this trade-off, but when there is no traffic, we should try to turn off as much as possible.
Right, so what you're saying is really, I mean, turning off subcomponents or subsystems on a fairly short time scale, might be even down to frame level or millisecond level, in order to save as much of energy in the circuitry as possible, and then at the same time utilize whatever knowledge is available regarding how we can predict when these resources are needed again, so that the system can wake up appropriately. That's an interesting prospect. Now, we talked a lot about putting devices and components in the systems to sleep, but if we focus still on the active mode, where, say, the physical layer is fully loaded, we have lots of devices that are served simultaneously, and they all want to get the maximum possible data rate under the power constraints that we have and the interference situation that we are in, and so forth. What can be done to improve the efficiency in the active mode?
Yes. So then it could be important to measure energy efficiency in a way that we can actually quantify and compare different types of methods. And one common way of doing that is to compute a benefit cost ratio, which is like the data rate that you're delivering divided with the power that you are consuming at the time, and try to...
So the data rate divided by the power consumed as some kind of metric of how energy efficient the system is?
Yes. And then that becomes, in the end of the day, a metric in bit per joule of energy that we are consuming. So that is...
right.
And then depending on what kind of traffic we're having, we have different number of bits, but it is then determining how many joules that they are consuming. And when it comes to legacy networks, they have often been built in such a way that there is a large amount of power consumption when there is little traffic, and then it increases just a little bit with the traffic. So there is no real connection between these two different things, which means that you to make it energy efficient, you want to have high load in terms of that type of metric, because otherwise you're just consuming a lot of energy that is not used for anything useful. And this was, at some point, it was claimed to be a good thing. Look, the traffic has grown this big amount, but look, the energy consumption have barely grown at all. But it's actually a bad thing, because you want to have this kind of linear behavior between if there's no traffic, no energy consumption, and when there is a lot of traffic, the energy consumption could be relatively high, to keep this ratio more or less constant between high load and low load.
So you're saying the key here is to keep this ratio, this metric, that was again the energy in joule consumed per information bit, to keep that as constant as possible over time? Is that like the goal that one should optimize for? You're
exactly
saying?
Ideally you would like to achieve that, since you dimension your network for these peak hours that I mentioned earlier, and then you know that part of the time you will have 5 to 10 times less traffic. So you want to have a rather smooth energy efficiency, irrespective of if you have high or low load for the moment.
Right. So you really want to smoothen out, in a way, the not only the traffic load, but really the energy efficiency in joule per bit. Here, you're saying, okay, that sounds like an interesting and somewhat new type of optimization criterion that I suppose would spark also lots of research and development into methods for how to allocate resources. I mean, not only radio resources, but potentially or probably also hardware resources in the systems.
Yeah, precisely. So if we just think to start with about power that we are using for the radiated signals, then if we have a certain power budget, this is the maximum amount we can radiate, then the amount of data that we can transfer is not growing linearly with when we are varying the power. We typically have the data rate is a logarithmic function of your signal to noise ratio, and up to a certain point it might pay off to increase the power, that you're transmitting with, so that you get a higher data rate. But after a while, the power consumption is growing, but your data rate isn't changed very much. So from that perspective, you come to the point where you don't want to use all the power all the time, even if you have traffic.
Right. Is that because the payoff in Shannon capacity is only logarithmic in power?
Yeah, exactly.
Or is this, so the capacity grows as log of the transmitted power, more or less.
Yes, and if one only
approximation,
if one only considers the transmitted power and the data rate, then one can show mathematically that you actually don't want to communicate at all, because then you get the highest energy efficiency ratio, and that is a sort of a artifact by that there is all of this other hardware component that you were mentioning that is consuming energy as well. So if you put those into the picture, you get a different answer. So this energy efficiency ratio becomes very sensitive to modeling, which is one of the issues.
I can imagine, and that's really an odd anomaly, right? That the optimum solution is to shut everything off and nobody communicates with anyone. That can't be, so there has to be a flaw somewhere in the model. But it does seem like accurate mathematical and accurate modeling of the physics here is going to be highly important in order to reach solutions that can substantially improve over what we have today. So I have always been thinking that one of the key elements or key enablers for improving the energy efficiency of wireless links is massive MIMO. For the simple reason that with massive MIMO we get a significant array gain. I mean, with 100 antennas we get a 20 dB, which is a factor 100 array gain, which effectively translates into a savings of radiated power by 100 times. Everything else equal. And we also know that in massive MIMO, when we multiplex to many terminals in the cell, then typically the vast majority of the power spent is spent on serving the most disadvantaged terminal that is typically in the cell border or in a deep fade somewhere. I mean, in the basement of a house or somewhere, right? So 99% of the power is spent on serving that poor little terminal out there at the border, at the cell border. And the rest of the terminals in the cell can almost just join for free because we have the multiplexing gain, and so little extra power in comparison is required to serve them simultaneously as well. So that has been, I suppose, my view on energy efficiency, that, well, if radiated power is important at all, then massive MIMO has to be the solution for the very reason that I just outlined. Is that do you agree with that, or are there other aspects here that will come into play?
I think in general I agree with this, and I have been studying this in some detail in the past as well. And one needs to keep in mind all of the things that are consuming more energy when you put more antennas into the system. So yes, you get the beamforming gain by adding more antennas to your system. So then you can effectively get the same received power by radiating less power. But you also have consumption in the additional radio frequency change that you need to have there. So at the end of the day, it's sort of like the received power is proportional to the transmitted power multiplied with the number of antennas you're using for beamforming. So and both of these factors are consuming energy. So there becomes some kind of optimization problem there as well, where you want to find the right trade-off.
Absolutely. So really what you're saying is that the power consumption of the actual radio frequency transceiver chains doesn't scale linearly with the radiated power. So there'll always be some, say, overhead or cost associated. When we scale down the power, then we also scale down the efficiency typically. And that will penalize in to some extent solutions that rely on, well, massive MIMO or many antennas in general. There certainly is such an effect, which is important to model here, I suppose.
Yes, and then there is this saying in the business areas that you have to spend money to make money, and here you have sort of the thing you need to spend energy to make data traffic or to be able to deliver that. So if you are using massive MIMO to try to make the system more energy efficient. It will for sure, or most likely at least, consume more energy, even if we can design the hardware more efficiently in the future to cut some corners utilizing good properties that MIME technologies have. We probably will consume more energy, but the benefit would then be that, yes, you get more energy delivered with beamforming and you get the multiplexing gain that you described. So if I can just find the right trade-off between these things, we can get a much better energy efficiency, but it will be achieved by having higher data rate and more energy consumption.
So really what you're saying is that if you compare, say, classical or old base station to a massive MIMO base station, well, the massive MIMO base station is going to consume more power in terms of, I mean, just the electricity it draws from the grid, right? Maybe 10 times, or I don't know, but a few times. On the other hand, at the same time, it will deliver 10 or 100 times more in terms of bits per second. So the energy efficiency is still more favorable with a MIMO solution.
Exactly, and since the data traffic is growing all the time, this is what is really important. And this is something we have seen in other fields in the past also. There is something called the Jevons paradox that, for example, when cars become more fuel efficient, people are also using them more at the same time. So we are never really seeing that decrease in the carbon emission from car, at least until now with the electrical cars. And the same thing here, we need to deliver a system that can deliver more data traffic, because that is what people are asking for, and then we'll consume more energy, but let's consume more energy in an intelligent manner so we push up the energy efficiency.
Right, so we talked a lot about broadband here now, and active mode and delivering many bits per second, right? So how about massive machine type communications that we touched briefly upon earlier, and the Internet of Things, where I guess the vision is that we could have lots of small, tiny devices and sensors, right? I mean, it could be hundreds of them in a home or in a garden, or thousands or millions in a city, or not to mention, I mean, out on countryside and in factories and so forth. And these devices would have typically very little to say, in the sense that they would be sleeping for most of the time and then wake up occasionally and maybe respond to some requests from the network or send a few bits of data from a sensor reading or something. What will be, you think, the energy efficiency considerations that have to be made here when IoT takes off for real?
Yes. So you mentioned the channel capacity earlier, and I did it as well. And that is sort of, whenever you use that metric to analyze things, is based on that you're transmitting a lot of data. And this is not the case here. So then it's really about trying to design efficient transmissions in terms of energy efficiency that is going on very quickly. And one option is that if you transmit just a small packet of data, then all of the hand shaking that needs to go on and say, oh, I would like to transmit, I'm raising my hand, oh, it's your turn now, you get these resources and this and that, and then it might be that part of the entire communication protocol consumes more energy than the actual transmission of the data. So then you can afford being less efficient in the data transmission if you can cut away that extra protocol in the beginning, and on purpose design something that is not so spectrally efficient but still consumes less energy. And then using very simple solutions, the devices are scheduled in advance to be transmitting at particular times, or wake up once per hour at least around a particular time to transmit something, and only transmit a small packet with some simple coding, things that are not requiring very much of hardware components. There's a lot of things to do that cut corners in the protocols, but it still consumes less energy.
But really what you're suggesting here is that the random access protocols themselves might be more significant in terms of energy consumption than the actual data transmission, right? Which calls for new solutions. I suppose grant-free random access is one such solution, where devices just, well, they stay asleep most of the time, but now and then they wake up and they have a data packet to send. and they just send it. I mean, they pick an appropriate channel code and a pilot signature sequence or something like that, and then they just send it and hope for the best, and then they fall asleep again. The network listens and decodes these transmissions, and in case transmissions collide, then, well, you rely on advanced signal processing algorithms and on MIMO arrays to resolve the collisions. And there is no, or not necessarily here, a transaction of the form that, the device first sends a preamble and asks for the transmission grant and gets a response, and then sends something and gets an acknowledgement, and so forth. So that's an exciting prospect with grant-free random access, and something that might indeed be coming for Internet of Things in beyond 5G, and which, as I understand from you here now, also will have significant implications on energy efficiency.
Yes. So in a way, you cut down a bit on the robustness, because you might not always be able to decode the signals, and then you're moving a lot of the energy consumption to the base stations, where they need to run these more advanced protocols. But but since you anyway are hopefully going to deploy this big arrays with massive MIMO with all its capabilities for mobile broadband application, we can utilize them for this aspect as well.
Yeah, sure. I mean, I think it can be safely assumed that all future wireless infrastructure for, say, cellular communications will comprise massive MIMO arrays in one form or the other. But the energy efficiency aspect here of the IoT devices is really on how to cut back the energy consumption of the devices and thereby save battery life, perhaps more so than cutting back on the energy consumption in the infrastructure. Although that, of course, is also important.
Yes, and even if you're only transmitting, or even if you transmit as often as every 10 seconds or so, if the transmission burst is extremely short as well, then if you add up the energy consumption, you might be running this device on a battery for 5 years, or at least until the point where batteries would anyway starts to discharge, so that you're limited by that, not by the radio.
Right. So where do you think we should start? I mean, if we look at the infrastructure side and we set the goal of improving energy efficiency with this metric that you proposed, joule per bit, by, let's say, 10 times. How do we go about that? I mean, do we start with the radio access, or do we start by densifying the network and put more and smaller base stations, or what are the real solutions here, if you were to summarize that?
So I was trying to do some analysis of this a few years ago, because I also had the belief that some kind of massive MIMO solution would appear naturally, but I wanted to formulate optimization problems, some kind of mathematics that would hopefully deliver what I was predicting as the output. And what I saw from those cases when I tried to analyze the data rates, analyze the power consumption, different things, was that if you build a big cell, if it's a macro cell, if you say that you have many kilometers of range, then the main consumer of energy will be the power amplifiers, because you need to transfer with very high power. And yes, you can add antennas to it, but the power consumption will still be large. So then cutting down on the maximum ranges, by putting up more base stations, will be a more efficient way of reducing the total energy consumption, because the distance to the cell edge will be smaller. And in a way, we have this concept of path loss exponent, saying that the power is disappearing with the distance to the power of 3, 4, something like this. And if you can cut all the distances by a factor 2, you're saving a lot in how much energy you will have on the edge of the cell. But then when you come to a point when you have densified so that you are not that limited anymore by the radiated power, the other parts of the hardware consumption is starting to be equally important. Things like what you're consuming for processing in the analog or digital domain. That is when it becomes useful to use things like massive MIMO instead of densifying in order for sort of take this power consumption that you have in the base station and share it between many users. You cannot really compress it very much, but if you increase it a little bit by adding more RF chains and then you multiplex users, you are effectively consuming less energy in the analog and digital parts per user than you would do before. So sort of sufficiently small cells, and that is typically of the size that we already have in urban areas. So that's why it makes a lot of sense already now to replace those base stations with massive MIMO.
Mm-hmm. So what you're saying here, I mean, the thesis that you're putting forward is really that, well, densify until radiated power isn't the dominating part of the energy consumption any longer. And then at the density that we reach, say, equip the access points with massive MIMO arrays, which is I think, very crisp and useful conclusion from your papers here, that this is how to think about how to optimize. I mean, in rather general terms, how to think about how to optimize for energy efficiency. Densify until radiated power isn't the dominating cost any longer, and then use massive MIMO.
Yeah.
So speaking of, I mean, you mentioned here, I think, path loss and covering large distances and so forth. Then my understanding is and has been that, well, I mean, obviously the physics doesn't change, right? There's nothing we can do about the speed of light or about the path loss. In fact, the path loss rather increases once we, or at least the to be more accurate, the effective area of an antenna decreases as we go up in frequency, right? But I mean, path loss is there as a consequence of physics principles. So while the physics remains unchanged, technology improves a lot in the sense, I mean, in terms of actual RF and hardware technology here, perhaps especially digital electronics, but also the analog. So what implications? I mean, do you agree with this view? And if so, what will be the implications if we extrapolate? If we think of a world where, well, the path loss hasn't changed, obviously, right? But digital electronics has become another 10 times more power efficient, and perhaps analog electronics has also become a lot more power efficient. So how will this impact the way we think about energy efficiency, and more importantly, how will it impact how we should design systems, you think?
I think this is the right way of approaching this problem looking forward as well, that we have these three types of energy consumption. Is the radiated power, and when it comes to radiated power, also what is burned away in the power amplifiers, which is typically 4 times as much as you're radiating or something like that. And then you have the digital processing and the analog. And I totally agree that digital processing is becoming so much more efficient, so that in the future we will not have to care very much about it. And when we also are putting a lot of things together as a system on a ship, then all the losses that was going between different ships in the past is also disappearing. So if we would then think about the future where we don't need to care so much about the digital processing, as long as we're not creating super crazy algorithms that have exponential complexity, all the linear complexity algorithms are easy. So what will we do then? Well, then we are left with analog processing, which is it's not going down as quickly. I'm not a hardware designer, but as far as I understand it, you should only expect a few percent of improvement over time there, as compared to, in orders of magnitude, improvement in digital processing. But since it anyway is going down, while the radiated energy is, as you said, determined by the physical world around us, and the power amplifiers are not getting that much more efficient. So then what can we do to get the radiated energy down? Well, that is once again coming back to the things with MIMO. Deploying more antennas at other locations, which would increase the analog processing, because you have all the radio ships, radio equipment connected to to the antennas, but it allows you to cut down on radiant energy. So I think that is what we will see, that with time, digital processing is not a big deal, but it also enables you to use more antennas and still be more energy efficient.
Yeah, I mean, it's hard to argue with this conclusion, right? And also, of course, using MIMO and exploiting really the gain resulting from constructive superposition of electromagnetic waves. That's all what that's about. So how about the computing infrastructure? I mean, there seems to be a large push towards centralizing computing operations or infrastructure. So I'm thinking of moving to the cloud and moving computations. I mean, in Cloud Run, for example, the idea is that you have much of the processing going on somewhere else than where the antennas are located. Are there benefits in terms of energy consumption from doing all that, or is that something you can comment on?
Yes, to some extent there is benefits, and I think in the beginning I was talking about identifying bottlenecks and try to consolidate hardware, and this is what it's really about here, to say, well, if we have this large load variations over the day and also between cells at the same time of the day, then it might be unnecessary to have a lot of compute infrastructure, meaning in this case baseband processing. Every base station have their own hardware, which no one else can utilize, and if most of the time there's not much traffic there, then if you can have some joint compute infrastructure, you might be able to let 10 base stations share 5 or 4 times the processing that they would have individually. So that could be a benefit, but then it's not necessarily either a benefit, because there is also energy consumption when you're moving information from the physical site of the base station to the cloud. So something is consumed over the fiber connections or whatever connections you're having. And then cloud computing in general, it's also about trying to utilize general purpose hardware for service, which are efficient when it comes to other general purpose type of processors, but you always have this kind of thing that if you design a dedicated circuit like an ASIC for a particular purpose, it will be more efficient. And I think this is what you can see when it comes to the massive MIMO base stations that some of the vendors now, Ericsson was presenting some new base station earlier this year, that they are on purpose putting some of the baseband processing in the antenna box, because that is where you can do it more efficiently with an ASIC, and then some things are moved to some kind of centralized point as well.
Yeah, of course. I mean, it makes perfect sense, right, to design application-specific circuits that sit close to where the data are generated and optimized for energy efficiency. But it, as you explained, it's also clear that there are other potential benefits of actually shipping over the data to a central location and process it there, to be able to share resources, perhaps most importantly.
Yeah, and we have focused a lot on the energy efficiency here. One could also talk about cost efficiency, and that would probably be a different episode. And to some extent, these things are aligned, because energy cost is also creating... I mean, if something is energy efficient, it consumes less energy, so there's less energy cost. But maybe for decentralized type of infrastructures, is also cost savings in terms of hardware that you're going to buy.
Certainly, there is a trade-off across multiple dimensions here, right? I mean, quality of service on one axis, energy efficiency on the other, cost on the third, and probably others as well. So, as a final topic that I'd like to touch upon today, energy harvesting and wireless power transfer. And that's really for small devices, call them passive devices or not, but for small devices in IoT applications. Is this something that will be coming, you think? And how will it, if at all, have an impact on energy efficiency in the networks?
So energy harvesting in general is a very good thing if the harvesting is efficient. So if you have a big power plant, it has its efficiency, but then you have a lot of losses along the way from the power plant to the edge where your network infrastructure is. So if the device is grid connected, well, then you will still be losing, say, 10% or 15% of the energy along the way in different kind of losses. So from that perspective, you can put energy harvesting at the edge, then you will get away with those losses, and then it might also be a renewable type of energy harvesting. And then if you're not connected to the grid, then it's sort of the trade-off between how much can you store in the battery and how much can you increase the duration of the device by harvesting the energy. And then when it comes to wireless power transfer, the problem with power transfer, if we are the ones on purpose who are radiating the signaling, I mean, if you are harvesting from the sun, it's there, so it sort of comes for free. But if we are going to beamform energy for the purpose of an IoT device being the one harvesting, the efficiency will be extremely low. I mean, even putting your device on this kind of charging mats that we have on iPhones and all other devices are now pushing that, we should have this kind of magnetic charging, QI charging kind of things. These are inefficient. They might only have an efficiency of 50%. So already there we start to lose things. And then if you wirelessly beamform signals, you might only have an efficiency of 0.001% or something like that, even over short distances. So wireless power transfer with radio frequencies is extremely inefficient. But there might be cases where it's the only way.
Mm-hmm. Right. So, I mean, there are really several separate issues here, right? One is that wireless power transfer has a very low, say, coefficient or very low efficiency. Notwithstanding, it might still become an important technology in order to support devices that are entirely passive and don't rely on a battery for their operation. But in terms of energy efficiency for the network as a whole, wireless power transfer is probably not going to make a big difference. And also the harvesting techniques that you mentioned here, well, they certainly will contribute a little bit if you can, use harvest from vibrations or harvest from ambient RF or harvest from with solar cells from the sun. But in comparison to the power consumed in total in the network, the contributions from the harvesting is probably going to be quite marginal, so it won't impact like the overall energy efficiency of the network. However, it will have potentially a huge impact on these small devices that don't need a battery anymore, or even edge equipment that can be made to operate without the connection to the grid. Does that summarize well?
I think so.
The conclusion you think here?
And I could add one more thing, which is if you think about base stations deployed in rural areas of the world where you are not connected to the grid, then it might be that you're burning diesel in order to be powering them. And at those specific locations where you have very inefficient you're producing a lot of greenhouse gases from the energy production locally, then if you could cut down on the energy consumption to the point where you can use solar panels instead, well, then that would be a great solution.
Yeah, of course, sure. Great. Okay, I think we are about to close up here. I had a final thought, and that is regarding artificial intelligence, and to what extent that you think it will be, say, an important enabler in order to improve on energy efficiency.
I think it is an important part of it, and it is actually one of the sort of great applications of this. So once you have deployed the network and you are stuck with what you have, now you can try to tune your protocols, and then you have all these things that are have statistical patterns user behaviors in different parts of cities, how they are varying over the day and over the year and things like that. You can try to learn those kind of statistical behaviors and use them to improve things like to which of the sleep modes should you utilize. Should you go into short-term sleep, deep sleep, or something in between, and when should you do that, and other ways of tuning your different protocols. If you have these IoT devices that are consuming or that are not transmitting very often, can we configure them in a way so we learn to avoid collisions based on the traffic in a particular area? So there is a lot of things here, I think, where AI could be useful.
Absolutely. I mean, using machine learning to model how users behave, and then using these models in turn to predict, say, future activities, and rely on those predictions in order to optimize how the system should operate. Yeah, that's an exciting prospect, I think. With that, perhaps we are approaching the wrap up for today. So thanks a lot, Emil. This has been great fun as always and very educational. Also, as always,
thank you for this conversation, and I appreciate a lot all the comments that we are getting from our listeners as well. So keep on listening and give us feedback and suggestions on future topics. And even if we are not covering them immediately, we are writing them down, and we might be covering them in future episodes.
Absolutely. So don't forget to like and subscribe to us on YouTube, and see you next time.
Bye-bye.
Bye.